let us now see the mathematical expression of the unbalanced voltages and the balanced line voltages. Okay. So, let us represent this balanced line voltages by this equilateral triangle having magnitude of small a this. So, these are the three equilateral triangles which are formed from unbalanced pole voltages having lengths L1, L2 and L3 here. So, if you have such triangle, then it is possible to get a relationship between A and L1, L2 and L3. That means, a relationship between the unequal pole voltages and balanced line voltages can be obtained, and it can be obtained by using the basic functions of coordinate geometry, and you can write the equations. So, if you take the x and y axis like this, then you can write down these equations L1 square and L2 square and L3 square. They all come from the basic coordinate geometry, and by solving 1, 2 and 3, we get a big and complicated expression of small a as a function of L1, L2 and L3. Okay. This is the expression here of the balanced line voltage as a combination of the unbalanced pole voltages magnitudes. Okay. So, if we see this expression, additionally we also can obtain the phase angle between the pole voltages. So, this theta 1 is this one, theta 2 this one, theta 3 this one, these expressions here, which are these angles which is needed by the pole voltages. So, it is no longer 120 degrees, it is given by theta 1, theta 2 and theta 3, and these angles are obtained by this expression here, and this will give us the balanced the phase angle required between the unbalanced pole voltages. Now, one more thing, there is a plus minus term here. So, there are two equations, there are two values of A possible. One value of A will be a smaller value and one will be a larger value. We of course would like to take the larger value, because we would like to maximize the line voltage when there is an unbalance or when there is an unequal pole voltages. Now, if so we generally take this plus sign here, okay, and do not take the minus sign, although minus is a possibility. Now, if we observe this equation carefully, then we must understand that this term within the square root, this must be greater than equal to 0. Okay. So, this must be greater than equal to 0, that is what we have written here, and if we solve this condition, or if this condition is only satisfied if this situation or this condition is satisfied here, this mathematical condition is satisfied, then only the under root term is greater than equal to 0. So, what does this mean? It means that in order for this equilateral triangle to be formed, L1 should be, or L2 plus L3 should be more than L1, L1 plus L3 should be more than L2, and L1 plus L2 should be more than L3, which means the sum of two pole voltages should always be greater than equal to the third one. Only then the balanced line voltages can be obtained, or the equilateral triangle can be solved. These all come from the basic geometry of the properties of an equilateral triangle. What does this condition say? This condition tells us that how many cells can be bypassed in order to produce a balanced line voltage. Okay. How many I can go on bypassing? I cannot go on bypassing for any numbers. Okay. So, for example, let us take the combination 555 and the value of A that we will obtain. If I put into that formula, the value of A will be 8.66. Under this condition, we can see that the sum of two phases, sum of two, that is 5 plus 5 is always greater than the third one, and so the equilateral triangle is formed. It is possible to form the equilateral triangle. If you take some other fault condition, say 554 means 5 cells in A phase, 5 cells in B phase and 4 cells in C phase, then we see that the magnitude of A is 8.04, and here also the at any point of time the sum of two sides is more than the third, and so the triangle can be formed. It is also true for 543 and 532 conditions, but if we take the fault condition corresponding to 522, so that means we have lost 3 cells in B phase and 3 cells in C phase, then this condition will be violated. 522, under this condition 522, this will be violated, and under that condition it is not possible to form an equilateral triangle. That means we can never get balanced voltages. Of course, we can get one balanced voltage, that is 222. We can go up to 222 and then we can get a balanced voltage, but with 522 it is not possible to get a balanced voltage. Okay. We can of course go to 422, we can go to 322, but we cannot get a balanced voltage from 522 combination. Okay. So, this is the, so the equation tells us the limit up to how much the balancing can be done. As I told you that once the pole voltages have become unbalanced, then a potential difference between the load neutral and converter neutral starts to appear, that is this VNO voltage. Okay. And it is a common mode voltage, because you can see that VAO is equal to VAN plus VNO, and it is same for all the 3 phases. So, this VNO voltage is a common mode voltage. So, from the previous equation you can get the magnitude of this VNO, and that is given by this expression here. So, how much of common mode voltage is getting applied can be found out from this expression here. So, we are showing here some simulation results. Say suppose first we have a balance condition, say 555, and these are the reference signals. For simplicity, we have shown the reference signals also going up to 5, length of or height of 5, we have shown it like this way. So, the pole voltages are something like this, which are balanced, so are the line voltages, are perfectly balanced during 555 condition. Now, when you have a 543 condition, then the reference signals have become unbalanced, 5 here, 4 here, and the blue one is 3 here, 5, 4, 3, and we see that a common mode voltage has started to appear. Okay. The pole voltages you can see are unbalanced, 5, this, the red one, yellow one and the blue one, they are unbalanced, the pole voltages. However, the line voltages are completely balanced here. and so will be the phase voltages on the load or on the motor. The phase voltages will also be perfectly balanced. So, from an unbalanced converter, we are now able to generate a balanced line voltage which can be fed to a motor. However, the magnitude of the voltage obtained here is less than the 555 condition. To go one step ahead, it is possible to maximize the balanced line voltage A. We have got an expression of A here as now. What is the maximum value of A that we can get? Okay. What is the maximum line voltage that is possible to obtain from an unbalanced converter? That can be seen by differentiating this expression. We have not shown this in this slides. If you differentiate it and try to maximize the value of A, then we come to a condition which says that the maximum line voltage which is possible, and that value is given by this one. A max is equal to L 1 plus L 2 plus L 3 minus max of L 1 plus L 2 plus L 3. Okay. How does it happen geometrically? You see here that the maximum line voltage will be obtained if this point O sits on one of the sides of the equilateral triangle. So, then this is one pole voltage, that is CO, another pole voltage is BO, and the third one is AO, and this will give us the maximum line voltage. In fact, there are several possibilities of this point O. Actually, the point O is a degree of freedom here. It can move at many places. Okay. And this degree of freedom, we are not going to discuss this here, can give us many interesting results, this degree of freedom of point O. Now, so what does this mean, this A max? A max is L 1 plus L 2 plus L 3 minus max of L 1 plus max of L 1 L 2 L 3. So, with a say 5-4-3 combination, the maximum voltage that is possible, that is A max, is 7. Okay. So, that means 5 plus 4 plus 3 is 12, 12 minus max of 543 is 5. So, 12 minus 5 is 7. So, maximum line voltage that is possible with this converter during unbalanced pole voltage is 7, and say of course, with 555 combination the maximum line voltage possible is 10. As I was telling that this point O is something which is kind of like a degree of freedom. Okay. The point O is not fixed, it can move. There are many applications of this movement of the point O. Okay. Typically, a lot of research work goes on here, that so far we have talked about the motor drive application, but suppose this cascaded edge bridge converter is used for feeding power into the grid from PV cells. Okay. Suppose each cell of the cascaded edge bridge converter is connected to a PV panel or a series of panels. Then each of them, each of the cells is, since they are connected to PV panels, they can feed power, and we get a high voltage with the help of the series connection of the cells, and then directly it is possible to connect the PV panel or the PV source to the medium voltage grid. It is possible, but the PV panels can produce different powers. all these PV panels can produce different powers, and so we have an unbalanced power generation among the phases. How to balance those powers? Because we do not want an unbalanced current to be injected into the medium voltage grid. So, under that condition, this point O is something which we play around with. The point O can change the power flow in each of these legs. It can redistribute the power flow. Okay. So far we were talking only from the voltage point of view, but you can conclude that as we change the point O, the power flow through each of these three phases are getting changed. PAO, PBO, PCO, power through A phase, B phase, C phase are getting changed because we are changing the point position of O, and thereby VAO, VBO, VCO are changing. So, if one phase is giving more or giving less, you can redistribute, you can balance the power flow and can do many things. We are not going to talk about it, but it gives, this discussion tells you that there are many possibilities by using this degree of freedom of point O, because point O is the converter's neutral point and it is completely floating. Okay. It gives you a degree of freedom. So, we will conclude the discussion on cascaded edge bridge now here.